Okay, so gave you your list. Talk about what those pieces mean along the way, but we're going to finish up single replacement here, and then give you a chance to practice a few. Talk a little about the lab tomorrow. Okay, so single replacement. One thing replaces another. Start off with one element, one compound, end up with a new element, new compound. Cutting in at the dance. Okay? Well, we cut in, higher replaces lower on the activity series. H is the problem, okay? Because H shows up in two places. It shows up in acids, and it shows up in water. Okay? So if it's an acid, everything higher works. It says so right on there. Acids, acids, acids. Okay? Okay? Second tier. So up here, only the first ones are the most active. They'll react with cold water. And you'll notice what's in this list is lithium, rubidium, potassium, sodium, all of the alkali earth metals, all the alkali metals and some of the alkaline earth metals. SrCa, zinc's here, Mg's here. I would suspect barium's up here as well. They just didn't put it on the list. Okay, so barium's going to be in this region, right? Oh, there it is, up there. It is up there. So we got alkaline earth metals and alkali metals. Yeah.
How come lithium and sodium and potassium are like all like super reactive and hydrogen won't react?
Because charge on the nucleus. Okay, when lithium has a 1+ charge, it's got a 3+ nucleus. Okay, it's all about charge on the nucleus and stability. So, I think this is the right video. So, okay, so this is sodium. Okay, and this you cut it. If you cut sodium over time, it actually reacts with the air. When it comes back here in a second, in 3, 2, 1, scratch. Come on, scratch it. Come on. So that's what I mean by you just set it in the air, you scratch it, you can see the shiny underneath. It tarnishes in air. Okay, that's potassium. Oh, no, I got that wrong. First was lithium, that was sodium, this is potassium. And potassium tarnishes as fast as it hits the air. So as I go down the alkali metals, they react more and more with air. Okay. So, you're going to put the stuff in the water. That's lithium. Piece of lithium dancing along the top of that. Okay. Sodium. It melts and dances along the top. Okay. Come on, it's exciting for a second. There. Now you put potassium in. It dances along the top and lights on fire. What the heck? What could be on fire here? Okay, that was cesium. No, rubidium. Cesium's next. That's rubidium. it reacts so violently it pushes itself back out of the water. And this is cesium. It's in a little container because it's kind of unsafe. That's cesium. Okay, so as you noticed, as I went down the alkali metals, they reacted more and more because they're more and more willing to get rid of their electron. It's about those periodic trends. Because you got more and more energy levels, that outside electron is less shielded, more shielded. More shielded makes it easier to take off. So cesium reacts quickly with water because its electrons all come off. Yeah, it would probably be worse, but you're never going to be able to do it. Because of its short half-life, there's always about a gram of francium on and in the Earth. But it's never the same gram. Because it's made by one radioactive decay. And then it decays really fast. But you got a problem there is the surface area issue. Okay? Because you've got a big thing, but it can only react on the surface. So, and as you get bigger, remember volume versus surface area, the volume grows as a cube, but the surface area only grows as a square. So it won't make as big a difference as you'd think. Now, if you could put a bunch of small pieces together instead of one big piece, you use multiple pieces, you get a whole bunch of small explosions because they would all have the surface and it'd add up to a big one. But you wouldn't want to put just one big piece because you wouldn't be touching as much water on the surface. Make sense? Oh, he bring back those surface area and volume things they talk about in bio all the time. Yeah, because they affect lots of stuff. All right, so, and they make hydroxides and hydrogen. So the flames you saw were the hydrogen burning. So what was the reaction when we put potassium into water? What did I make? Well, first thing is, we don't want to write water as H2O. In single replacement, we want to write it as HOH, hydrogen hydroxide. Because the potassium is going to kick off one of the hydrogens and end up next to hydroxide, and then hydrogen will be by itself. Can hydrogen be by itself? Nope. So hydrogen gets a 2, K is 1 plus, OH is 1 minus, so that's the right formula. I go to balance it, I got 1K, 1H, 2 H's. So I got to put a 2 in front of water. That gives me 2 hydroxides. So I got to put a 2 in front of KOH, which gives me 2 potassium, so I got to put a 2 there. But the flames you saw were not the potassium burning. The flames you saw were the hydrogen burning. And if you look carefully, they had a purplish tint because when potassium gets heated, its electrons jump up and they fall back down and give off violet light. Okay? So you saw a violet tinge to it because the potassium electrons were moving around. Okay? That's what's going to happen every time. You're going to take the H off, you're going to end up with a hydroxide and hydrogen every time. Okay? The next group down, if you heat the water up to steam, it'll happen. If you don't, it won't. They won't react with cold water. So they're active, but not quite as active. Probably not. I probably can't order it. The fact is, I have difficulty ordering potassium because potassium actually will make a superoxide if you let it sit too long in air. And a superoxide is a contact explosive. So that what happens is that it forms around the lid, and all you have to do is turn the lid and it blows up. So when I worked in Rialto, first thing I did is I went in the storage room and I saw an old body of potassium with a whole bunch of stuff growing on it. I called the fire department. I said, we got a problem here. This is going to blow up. Yeah, they came and took care of it, yeah. We don't want things blowing up in our storage room. But Okay. The next group will work with acids, but not with water. So acids are easy to knock hydrogen off of because an acid by definition is something that gives off hydrogen ions. That's its definition. So if it's going to give off those ions, it's going to be easier to replace. Water doesn't give off hydrogen ions, so you have to take it from the hydroxide. Make sense? From H2 on down, they won't react with hydrogen at all. In fact, hydrogen will replace them. So what do I mean by hydrogen replace them? Well, if you had, oops, I don't want subtitles. If you had H2 plus CuO, Cu couldn't replace H2, but H2 can replace Cu, so H is going to end up next to O, and Cu is going to end up by itself. Can Cu be by itself? Yes. H is 1 plus, O is 2 minus, so that's H2O. And then we have to balance it. That was hard. Okay. So you start off, so hydrogen can replace it. It can't replace hydrogen. So this won't go backwards. Cu will not react with oxygen to form copper oxide and water. Okay. Some of them are still reactive. They'll react with oxygen to form oxides. The reason the Statue of Liberty is green is because the outside coating is copper, and being exposed to the air has had it turn into a copper oxide. That greenish color is copper oxide, copper 2 oxide. Okay. And the lowest activity, they won't even react with oxygen. And I say they don't rust or tarnish. I got to disagree with it just a little bit. I know that over the years the silver will tarnish because I had to clean my grandmother's silver when I was a kid. We'd get it out every couple of years and it would be tarnished and we'd have to shine it up. But silver does a little bit. Platinum and gold, I've never seen a tarnish on platinum or gold. Okay. So that's why we use those ones on the bottom, as Peter said yesterday. We use those bottom ones for jewelry. Right? We use it for jewelry because you want your jewelry to shine. We don't want it to stain our finger green because oftentimes they make an alloy by mixing the gold, mixing these precious metals with copper. Copper oxide's green. That's where you get the green staining. And nickel oxide as well. Sometimes they use nickel too. Well, not nickel 2, nickel 3, but nickel also. Things made out of bronze tend not to rust because of the interaction between copper and zinc and how they fight for electrons. Because you got zinc in there, and zinc's up high. Mostly it's bronze statues, and bronze statues tarnish, so get a patina. So it's going to do some, but it takes a while. Okay, but here's the other place we use them for. Money. Okay, when before the middle of the 1800s, the only kind of money you had was coins that were really made of that. Were coins made of gold, coins made of silver. Okay. Well, if you see watch an old movie, an old Western, you'll watch the guy take a coin and bite it. Why would you bite it? Well, because pure metals are more malleable than mixtures. So if you leave your teeth print in it, it's probably pure gold. By how easy it is to put a tooth print into it, you can tell about how pure the gold was. Yeah. And you could tell for sure if it was fake because it wouldn't be as malleable. So they were actually testing it to see how good it was. Okay. Why did they pick those for money? Why not pick something up higher? Not because it's shiny. Because you sold it by weight, right? It was that many grams of gold. It was by weight. So if they tarnished, one of two things would happen. One, the tarnish would be an oxide that would stick to it, and your money would get heavier over time, which would make it more valuable when it wasn't any more gold. Nobody wants that kind of money. Want money to be constant. Okay? Or if they'd used something that reacted, it could have made an oxide that fell off, like rust. And then you'd be losing your gold all the time. You want something that's going to stay constant. That's why they pick them for money. Not because they're shiny, but because they don't change. I mean, you would not want to use sodium coins. You know, talk about the extreme. Washing your pants could destroy your fortune and your house. But so you want something that can't react. Okay. Make sense? So let's use those examples to go through a series. Al plus H2O liquid. Okay, first step. What category of reaction is this? Is it single replacement, double replacement, or single replacement combination, or decomposition? Single replacement. So we want it to be single replacement, and that means we need to use the activity series. So I need to find aluminum and hydrogen on my activity series. Will this reaction happen?
Yes.
Okay, aluminum is higher than hydrogen, so it can replace it, but not in water. Not in water. Yep, that's why I gave it to you. You don't have to memorize, you just have to know how to use it. Okay, so aluminum's higher, but it's not high enough because it said liquid water. And that's how you do it. So now, that's my next example. Now there's going to be a reaction because now it's water vapor. The way you make water vapor is make it hot, right? That's steam. All right. Okay, so now there's going to be a reaction. So see why those states of matter become important on this one. Okay, so aluminum is going to replace hydrogen, but remember, water is really HOH. So aluminum is going to end up next to hydroxide, and hydrogen's going to be by itself. Hydrogen can't be by itself, so I put a 2 next to it. I was supposed to ask you, but it's so automatic for me. Okay, aluminum is 3 plus, OH is 1 minus. So notice what we did. We did what the name said. We single replaced. Now we figure out subscripts. I need 3 OHs. Now I have the right formulas. Now I want to go balance. Now to balance this, we could just try numbers and that would work, but here's another way of thinking about it that might make it easier. Okay, you know that you have to make hydrogen hydroxide. So hydrogens have to equal hydroxides. Looking on the product side, when are hydrogens going to equal hydroxides? My hydrogens come in groups of 2s, and my hydroxides come in groups of 3s. They're going to run into each other when they're 6, right? See how seeing that ratio makes it a little bit faster to balance? They're going to run into each other at 6. So I know I'm going to have 6 waters with 2 ALOH and 3 H2s. And that gives me 2 ALs, so I got to put a 2 there. So seeing how I figure out the 6 waters made it so I didn't have to go through that whole doubling process. Because you would have come to a point where it was even and odd along the way. But since you know you had to use one hydrogen for every hydroxide, you're going to do that when they're at 6. The least common multiple. Right? Least common multiple. What about Al and HCl? Well, Al is going to try to replace H. Can Al replace H? It can replace it if it's steam, if it's water, but this isn't water, this is an acid. That's hydrochloric acid, right? It's an acid. It works with acids. It says acids right there. So it's going to work. So the aluminum is going to end up next to the chloride, and the hydrogen is going to be by itself. Can hydrogen be by itself? No. Al is 3 plus, Cl is 1 minus, so it's AlCl3. And you notice I'm at the same spot here. I got to have one H for every Cl. So I know they're going to run into each other at 6 again. But let's do it the other way without doing that. So the first thing I do is I put a 3 in front of HCl. That gives me my 3 Cls. And the only thing that's not balanced now is H's. Because it's 3 on one side and 2 on the other. What do you do in that situation? You double the first one, which forces me to put a 2 here, get my 2 ALs, which will give me 6 Cl, so I can put a 6 in front of HCl, and now I can fix the H2. So either way you approach it, you get the same answer. You still get that 6 in front of HCl. Both ways get you there. Looking for that ratio early might save you some time. Okay, so tomorrow you are going to actually do an activity series. You're going to try to figure out, where did my Edge browser go? Oh, there it is. Okay, you are going to do a series of experiments. So here's a simulation. Here's a simulation of the kind of experiments you're going to do. So, whole bunch of, you're not going to have 8 solutions, you'll have just a few, but here's the basic idea. You're going to have solutions, and you're going to have pieces of metal. Okay? And you're going to take, so I'm going to take a piece of magnesium, and I'm going to put it in each solution. And I'm going to wait. And then I'm going to remove them. Some of them reacted, some of them didn't. Right? If they reacted, that means the metal by itself was higher on the list than the metal in the solution. So it's easy to explain why MgNO3 and Mg did not react, because magnesium can't replace magnesium. But the fact that magnesium replaced zinc tells me that magnesium is higher on the list than zinc is. Magnesium's more active because it didn't end up alone. The more active one changes. If it's by itself and it changes, it's more active. If it's by itself and it doesn't change, it's less active. So if I put lead and let it sit, now I can remove them. Which one changed? None of them changed, did it? So that means lead is lower than all of those metals. Does that make sense? It wasn't strong enough to push up. It was a freshman, not a senior. Is that analogy? Okay, but if I put nickel in, nickel could replace lead. Shouldn't surprise us because lead couldn't replace nickel. If lead can't replace nickel, then nickel can replace lead. If it doesn't work one way, it works the other way. Right? So it does make sense. So if I'm making an activity series, right now my activity series, I know for sure that I got lead here and I got nickel there. And iron and tin are, oh, it worked react with tin too, didn't it? So tin and iron in there, so I got to choose between tin and iron. And the way I choose between tin and iron is I try tin and iron. So I put tin in, and tin reacted with the lead, but not with the iron. Or with the nickel, right? So tin is not strong enough to replace nickel, but it is strong enough to replace lead. And nickel, so that's why nickel could replace tin. Okay? And Fe, it replaced everything in here except Fe, right? So Fe is the highest out of these four. And then lead was lowest. And nickel, where did it fit in there? So nickel was higher than tin. So it looks like out of these we've got iron, nickel, tin, lead in terms of activity. Here's what's really going on. Okay? When I put the lead into the nickel nitrate, what's happening is nickel ions, 2+, are coming upon neutral lead and stealing the lead. They're not stealing anything. Right? There was no reaction. But if I put the nickel into the lead steals the electrons away from nickel. That nickel's now an ion, so it can go into solution. The lead is not an ion, so it comes out of solution. Ions are in solution. Ions are in solution. It takes the electrons away from the nickel. Okay, takes the electrons away from the nickel. That makes lead neutral, so it can't stay dissolved, it comes out of solution. Makes nickel have a charge. It's an ion, so water can hang on to it, and it can be in solution. Okay. That's what's going on. It's a fight for the electrons. It's really a way of measuring something close to ionization energy. It's not quite ionization energy because it's not a gas, and water stabilizes these. Make sense? Reasonable? Okay. So that's what's going on. So that's what you're going to do tomorrow. I will give you some metals. I will give you solutions with those metals in them. It's going to be your job to do the experiments to come up with the activity series of those metals. Make sense? So that's what we're going to be doing tomorrow. We'll do it with the droppers and little pieces because we don't need to see big pieces. All we need to see is there a change? Right? I don't know why the numbers got cut off on this. It's time to fix the machine, I guess. The left-hand side is not working. But you don't need to see the numbers.